Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. In today's video, I want to talk about a difficult subject, rheology. In particular, how rheology is applied to pharmaceutical materials. And if you're revising rheology right now, I thought it would be helpful to give you some hints and tips of the sorts of things you might need to know in order to be able to answer any rheology question that might come up on a pharmacy paper. So, that sounds good to you? Get yourself a drink. I, of course, have got coffee, and let's make a start. Rheology is a difficult subject. There's no getting away from that. But if you break it down into small chunks, each chunk becomes relatively easy to understand and the topic isn't that difficult anymore. The first thing, therefore, to understand is what actually is rheology in the first place. Rheology means the study of the flow and deformation of materials. So that's not too bad. What sort of materials are we talking about in the pharmaceutical world? We can have anything from pure liquids all the way through to creams, suspensions, gums, things you might ordinarily call semi-solid. We are not really concerned with true solid materials in the pharmaceutical world. Everything we deal with is a liquid or a semi-solid. Liquids and semi-solids are also examples of Newtonian and non-Newtonian materials. So, a good thing to be able to do in an exam is to be able to describe the difference between a Newtonian and a non-Newtonian material. So let's start there. We'll start with Newtonian materials because they are the easiest to define. For a Newtonian material, the shear rate is directly proportional to the applied shear stress. What that means is we apply a stress to a Newtonian fluid and it moves with a certain rate. Doesn't matter what it is. If we apply double the shear stress, it moves twice as fast. Triple the shear stress, it moves 3 times as fast, and so on. To characterise the rheological behaviour of materials, we therefore plot shear stress versus shear rate as a diagram. So, I have some axes on the board. Shear stress is on the y-axis. It has the symbol sigma and units of Newton meters squared. And shear rate is on the x-axis. It has the symbol gamma and units of seconds to the -1. Because for a Newtonian fluid, the shear rate is directly proportional to the applied shear stress, we will get a straight line when we look at a graph like this for a Newtonian fluid. So that's how we define a Newtonian fluid. How then do we define a non-Newtonian fluid, I hear you ask? And the answer is, it's the opposite. If a Newtonian fluid is one where the shear rate is directly proportional to the applied shear stress, a non-Newtonian material is one where the shear rate is not directly proportional to the applied shear stress, and the graph becomes a bit more complicated. There are lots of different types of graphs that you might measure, but in the pharmaceutical world, we are really concerned with graphs that look like this, or that look like this. It's kind of important from an exam perspective that you know what these types of behaviours are and also what type of materials give those behaviours and why. But I'm going to come back to that in just a second. For now, just remember a non-Newtonian material has a line which is not straight. It's going to be curved in some way. If you were to write that as the answer to an exam question, the exam question being, what is the difference between a Newtonian and a non-Newtonian material? Do you think that would get you full marks? The answer is nope, because there's one more thing that you can say, and that is that when you plot these graphs, the gradient of the line is equal to the viscosity of the material. Viscosity has units of newtons per meter squared seconds, or centipoise, and it's the gradient of this line. If we measure the gradient of the line for a Newtonian material, it doesn't matter whether we measure the gradient at a low applied stress or a high applied stress. The gradient is the same and therefore the viscosity is the same. So another way of defining a Newtonian material is that the viscosity is constant. On the other hand, if we look at the curves for non-Newtonian materials, let me pick this one first. If we measure the gradient at the start, the gradient is quite steep, so viscosity is high. And if we measure the gradient at a higher applied stress, the gradient's got shallower, so the viscosity has got lower. So in other words, this is an example of a material that's becoming thinner when it's being sheared. If we look at this type of behaviour, on the other hand, and we were to measure the gradient, we can see initially the gradient is very shallow, so the viscosity is low. And as we look at a higher applied stress, the gradient's getting steeper, or the viscosity is getting higher. So this is an example of material that gets thicker when we apply a stress. So, for top marks, if the question says, describe the difference between a Newtonian and a non-Newtonian fluid, you would say a Newtonian material is one where the shear rate is directly proportional to the applied shear stress, and a non-Newtonian material is one where the shear rate is not directly proportional to the applied shear stress. And also, for a Newtonian material, the viscosity is constant, and for a non-Newtonian material, the viscosity is always changing. Right, next thing you might need to worry about in an exam is what's the difference between shear thinning and shear thickening materials. So let's go there, starting with shear thinning materials. A typical question in an exam about rheology might say, draw the shear stress versus shear rate diagram for a plastic material. So what that means is you've got to understand what one of these graphs would look like for a plastic material and then draw it. Or, for argument's sake, the question might say, here is a shear stress versus shear rate diagram. What sort of behaviour is being shown? So then you've got to look at the diagram and work out what behaviour you are looking at. So you've got to try and understand what these curves are telling you. For a shear thinning material, there are two types of rheological behaviour that we worry about for pharmaceutical materials, and those would be plastic and pseudoplastic. As you might imagine, these two are quite similar. Pseudo means like, so plastic, plastic-like. Therefore, they are quite similar, and it's really important that you know the difference between them. So, given it's a shear thinning material, thinning means as we apply a stress, the material becomes runnier. Runnier means less viscous. Less viscous means the gradient of the line is getting shallower. So, we will end up with a curve that looks something like this. Gradient is high at the start, so the material is quite viscous, and then as we increase the amount of shear stress, the gradient is getting lower, so the material is becoming thinner. So right from the get-go, remember, any shear thinning material, the curve looks like this. What you then need to remember is, what's the difference between plastic and pseudoplastic? And it's a subtle difference. The difference is a pseudoplastic material will start to flow with any applied stress. So down here, doesn't matter how small the applied stress we're applying is, the material is starting to flow. But a truly plastic material, think about plastic material. It's got a kind of strength to it, and so when you apply a force to a truly plastic material, initially it resists that force and doesn't move, but when you go over a certain threshold, you break the bonds that are holding that material together, and then it starts to flow. And so what that means is, from the rheological behaviour, we don't see any movement of our material at low applied stress, and then there becomes a critical point at which the material starts to flow. And then we will see shear thinning behaviour. And this point here is called the yield point. So, the key difference between a plastic material and a pseudoplastic material is that a plastic material has a yield value and a pseudoplastic material doesn't. It's really subtle, and you've got to be able to look at these graphs and determine, is there a yield point or not? Because that's the key difference between them. Okay? The other thing you should be able to do to get good marks in an exam is to give an example of a type of material that exhibits these behaviours and explain why it does so. Okay, so there are a number of good examples, but the ones we used in class are a plastic material for a pharmaceutical. Remember, there's lots of materials in the world, but they're not really pharmaceutical, and we're dealing with pharmaceutical materials. Would be a flocculated suspension. Remember what that is. It's a suspension, so particles, and flocculated means they've got something around them, typically a polymer, which is coating those particles, and then the polymer chains are entangled with each other. And the effect of that is that those particles are kind of held in place because of the polymer entanglement. So when you apply a force, there's a resistance to that force, and you've got to apply enough force to kind of break those entanglements before the particles start to move. So that's the reason why a flocculated suspension shows plastic behaviour. Whereas a pseudoplastic material, a good example would be, say, a gum or a paste. Gums and pastes are quite semi-solid, much more solid-like than liquid-like. And again, if I think about a gum, for instance, that's going to have lots of polymer chains in it, which are kind of interlinked, but no real solid particles, which is why it's not a flocculated suspension. So although there's lots of interlinks, it's still quite fluid. And if you apply a force, the material is going to start to move anyway. And a paste is something that's it's got a high solid content, but with liquid around it. It's not got the polymers interlocking. So again, you apply a force to a paste, and that material should start to move. So, hope you can see from the exam perspective, you should be able to either look at a shear stress versus shear rate diagram and tell whether the material is plastic or pseudoplastic, yield value, remember, or you should be able to draw the shear stress versus shear rate diagram for a plastic or pseudoplastic material. And it's a good idea to remember an example of a pharmaceutical material that has these behaviour types. Right, there is one other type of material that you need to understand, and that is a shear-thickening material. So let's look at those. If these are the graphs for shear-thinning material, I hope you can imagine that the graph for a shear-thickening material is going to look the opposite. So if we draw the opposite, we will get something that looks like this. Or you can, of course, interpret that graph by looking at the gradient of the line. So the gradient initially is quite shallow, the material is thin, and as we apply increasing amounts of shear stress, the gradient starts to get steeper, or the material is becoming thicker. So a shear-thickening material has a special name. It's called a dilatant material. So if the question says, look at this shear stress versus shear rate diagram and say what sort of behaviour it is. If the graph is getting steeper, it's a dilatant material or shear-thickening material. Or if the question says draw the shear stress versus shear rate diagram for a dilatant material, you should draw something that looks like this. And then the principle is the same. What is an example of a shear-thickening material? And a good example, is the one we used in class, would be a deflocculated suspension. Deflocculated suspension, not a flocculated suspension. These are very different things. And the reason that a deflocculated suspension gets thicker is because initially you've got particles suspended in a continuous phase. Each particle is surrounded by liquid, essentially, so it's well lubricated and the material is easy to flow. As you start to increase the applied shear stress, the particles start to clump together and there's no longer any lubrication between those particles, and so they can't slide past each other so well, and the material starts to become thicker. So a good example of a shear-thickening material is a deflocculated suspension. So same principle, learn plastic, pseudoplastic and dilatant. Learn what they look like. Plastic, pseudoplastic, dilatant. And remember a good example of each type of behaviour. Flocculated suspension for plastic, gums and paste for pseudoplastic, deflocculated suspension for dilatant. If you remember those things, you're pretty well set to answer any type of question that might come up in a pharmacy exam, at least about rheology. If you really want to get top marks in a rheology question, there's one more thing that you need to get your head around, and that is time dependency. So I propose we look at that next. Time dependency is the hardest thing to get your head around when thinking about rheological behaviour. And the way to do it, at least in my mind, is to think to yourself, okay, to make one of these plots, what we need to do is take our material without any applied shear stress, so down here, and it's not moving, so it's at this point of intersection, and we start to apply a shear stress, so we will go up this axis, and as we go up, we measure how fast the material is moving, and we get a plot that looks like one of these. That's fine. Remember, the reason that the material is either thinning or thickening is because we are changing it in some way. We're either breaking bonds or we're losing lubricity between particles, but we're doing something to the material to change it. The question then is, okay, when we start to remove that stress, do the bonds that we broke form instantly, or does the liquid that we forced out between these particles immediately come back again, or not? If the change is immediate, then what would happen is, and I'll change colour to make this a bit easier, and I'm going to start with pseudoplastic materials. If this is what happens to the pseudoplastic material as we start to apply the stress, and we're breaking some bonds, as we remove that stress, if those bonds were to reform immediately, it will have the same behaviour on the way down as it did on the way up. So we could go backwards and forwards along this line because the material is reacting instantly to the stress being applied or removed. It's much more likely that if you've applied a stress to a material and you've changed it in some way, it's going to take a little bit of time to recover from that stress being applied. So if a material is being held together with some bonds and we apply some stress and break those bonds, the bonds have got to reform, and that's probably going to take a little bit of time. And that has a bit of a consequence for how the material behaves. And the consequence is that it will introduce a degree of hysteresis into the data. Hysteresis means not the same as we go in both directions. So, again, if I think about my pseudoplastic material first, if it takes time for these bonds to reform, when I remove the stress, I will get a curve that looks a little bit like this. This, I should put an arrow on it to remind us, is what the curve looks like as we apply the stress, and this is what the curve looks like as we remove the stress. How should you remember this from an exam perspective? And I think the way to do it is this. For a plastic or pseudoplastic material, the material is shear thinning. You apply a stress, the material gets thinner. If when you remove that stress, the material doesn't respond immediately as the stress is removed, it's going to remain thin. You made it thin by applying that stress, you remove the stress, it remains thin. In other words, this material should be thinner than this one. And if we think about that, if we were to measure the gradient of the line at the same applied stress, we will find on the way up the gradient is steeper than on the way down, which says the viscosity is higher on the way up than the way down. Or another way of doing it is to go, well, if I pick a particular shear stress value, which for argument's sake I'll pick this one, if I look at what the material was flowing like as we applied that stress, it was flowing with this shear rate. And after I've removed the stress and I look at what shear rate it's flowing at, it's looking at this shear rate. This one is faster than this one. So for the same applied stress, the material is flowing faster on the way down than it was on the way up. And that's because we thinned it and it's remaining thin. That is quite a difficult concept. I'm not arguing, and there is a video for the lecture on rheology that you might want to watch because it goes through that principle in more detail. I'm really focused here on what you need to do in an exam to answer a question if one comes up on time dependency. And I will also note that time dependency for a shear thinning material is called Thixotropy. So if you see the word thixotropic, describe a thixotropic material, it's asking you to draw the shear stress versus shear rate diagram for a plastic or a pseudoplastic material with hysteresis. And it's a good idea to remember what you've done is apply some stress, break some bonds, and it takes a while for those bonds to reform. A question might also say, well, talk through the time dependency for a dilatant material, for instance. And in this instance, dilatant means shear thickening. So it's the same principle. On the way up, we get a curve that looks like this as we apply that shear stress. As we remove the shear stress and we have hysteresis, we will end up with a curve which is slightly different on the way down. In this instance, on the way up, we've applied some shear stress. The material has got thicker. When we remove that stress, the material doesn't respond instantly and it remains thicker. That means if we compare gradients, we should see a higher gradient on the way down than on the way up. And also, if we look at the speed with which a material is moving for a given stress, let me, for argument's sake, I'll pick the same one. So if we go across, this is the rate that the material was moving at as we started to apply that stress. This is the rate that the material is moving at as we remove the stress. This is faster than this. So the material is moving slower when we remove the stress, faster when we apply it, because the material is thickening. So we've applied this stress, the material's got thicker, we remove that stress, the material remains thick. And because it's thicker than it was before, it flows slower. So I hope you can see it's flowing slower on the way down than on the way up. And that is just about all you need to revise to make sure you can answer a question on rheology if one comes up in a pharmacy paper. You might think to yourself, where is rheology important? And actually, it's important in a lot of formulations. So if you think about some of the undergraduate practicals that we do at UCL, you do a practical where you make suspensions. You do a practical where you make creams and emulsions, for instance. And in those practicals, what you're doing is you're adding excipients to a formulation and measuring how that formulation is behaving. And what you're actually doing is changing the rheological behaviour of those materials. You might not think it, but you are. So imagine that in an exam, the question said something like, what sort of rheological behaviour would you expect a cream to have? And how might you change it by adding excipients? You've got to think to yourself, what is it that I need a cream to do? So imagine that my pen here is a tube of cream and I were to take the lid off the cream. Do I want the cream running out on the floor or do I want it remaining in the tube? I want it remaining in the tube, don't I? So it's going to stay in the tube for a bit until the patient squeezes the tube to extrude the cream onto their skin. And then when they rub the cream into the skin, they're applying a stress, shear stress to that cream. The cream should move because we don't want it sitting on the skin as a hard lump, do we? We want it to flow and absorb into the skin. So you could look at one of these behaviours and you could say, well, actually, which one of these behaviour types describes a cream? You want something which is kind of thick at the start and becomes thinner as a stress is applied, but also we don't really want really hard lumps of cream. So the answer is a pseudoplastic material is ideal for a cream. It's got enough viscosity at the start, it's not flowing out of the tube, but as soon as the patient starts to apply a shear stress, the material starts to thin and allows you to rub it into the skin. And then you could think to yourself, well, how might I change the properties of a cream? I might add a polymer, mightn't I? If I start to add high molecular weight polymers, I'm going to make it thicker. If I add shorter molecular weight polymers, it'll be runnier. So just think to yourself, what sort of excipients you might add to formulations and how it changes the properties, because that will really allow you to start to describe how rheology impacts the formulation of pharmaceutical materials. So, I hope that helps. Don't ask me if there's a question on rheology coming up in the pharmacy paper, because I don't know. There may be or there may not be. You'll just have to wait and see. But anyway, I hope that helps a little bit. If there are some questions on rheology that you don't understand, drop me an email think about hitting the like button or considering subscribing because it really helps the channel. Otherwise, good luck with your revision and I'll see you again soon.